Okay, we have our second talk of the morning session. We have Willie Rush Lim speaking from Brown on a priori bounds via totally degenerate regime.
Thank you very much, everyone, for having me here. It's really a pleasure. 2 years ago, I was at this conference, the inaugural CNAM conference, and I was still a graduate student. And then 2 years later, here I am, and I'm very glad to be here. So today I want to talk about joint work with Jeremy Kahn on what the title is a priori bounds via totally degenerate regime. I'm not going to present any new theorems, but I will try to present some new ideas, which hopefully will result in more new theorems in the future. Okay, so we're just gonna go with some basics. I'm really just gonna be looking at quadratic polynomials, complex quadratic polynomials, and it can be normalized as fc z squared plus c, right? Where 0 is the critical point, and then its image is c, which is the critical value. And then the field Julia set is known to be the set KFC, which is the set of points in which the iterates stay bounded, so it doesn't diverge to infinity. And then the manifold set is the set of points in which the critical orbit is in the field Julia set. It remains bounded. Equivalently, it's also characterized by the connectivity of the field Julia set or the Julia set. Okay. So this is a picture of the manifold set. One of the conjectures is that the manifold set is locally connected. This is a central conjecture. It implies a topological model of the manifold set itself. It also implies the conjecture on the density of hyperbolicity in the quadratic family, right? So this is still a conjecture. It remains open, at least maybe hopefully for, I don't know, in the next few years it'll be solved, but who knows? Okay. So to really tackle this conjecture, we have to go a bit beyond quadratic maps, and this is in the realm of what we call quadratic-like maps. And quadratic-like maps, it has been mentioned a few times, and so what this is that we have a holomorphic branch covering F from U to V, and these two sets are disks. U is nested inside phi, and then so this is roughly the picture. U is mapped into phi as a branch covering, and this double branch covering has a unique critical point. And then we also are going to impose a condition that the field Julia set, is the set of points that do not escape the domain U. This is connected. Okay. And we have a remarkable theorem by Doherty and Hubbard that states that quadratic-like maps are really as good as quadratic maps, okay? In the sense that if we pick any quadratic-like map, so F from U to V, then there exists a unique parameter in the manifold set, so that F is really equivalent to F sub C. And equivalent here in the sense that there exists a QC conjugacy, a quasi-conformal map phi, so that it's really a conjugacy on the domain. And then we also have a further regularity that actually is conformal almost everywhere on the field Julia set. Yeah. And then here, there's also a uniqueness statement that this parameter C is really unique, and this defines then what we call a straightening map. Okay. The straightening map is really from the space of quadratic-like maps to basically maps on the manifold set. Okay. The proof is an application of quasi-conformal surgery, essentially. From quadratic-like maps, you want to try to fill in the rest of the disk so that it becomes the whole Riemann sphere. So you have a global map. And we have a notion of renormalization. And here, if we start with a quadratic map or quadratic-like map, it doesn't really matter. We say that it's renormalizable with a certain period, say P, if we look at the iterate, the pth iterate, so Fp, and then we can find domains A to B. So these are disk A contained inside B, so that this map, this iterate here defines a quadratic-like map. Okay? It defines a quadratic-like map. And then this is what we're gonna call, well, typically it's called a pre-renormalization of F. But then I'm just gonna, take a shortcut. I'm just gonna call it renormalization of F. Okay. Whenever we have renormalization, we can also look at the corresponding Field-Julia set of this renormalization. Okay, I'm gonna denote it by K0, and then you can try to take the iterates, and so K0 will be mapped into K1, will be mapped into K2, and so on and so forth until, say, Kp minus 1, and then it gets mapped back into K0. So this guy will have, it's going to be like a cycle of little Julia sets with period P. Okay. And then there are generally two types. So primitive, we call it primitive when the cycle of little Julia sets are pairwise disjoint. Okay. And then if there is intersection, then this is going to be satellite. It's going to be satellite. So the rough picture is the following. So the original map that we have is F. So this is some kind of big Julia set. But then inside, we may be able to find renormalization, which means that there exists some disks, say here A to B. And then you can consider the non-escaping set of the system. So it's going to be some little Julia set here. And then this may be mapped here. It might be mapped here until eventually it comes back here. So it forms a cycle. From the way I've drawn this, they are disjoint, in which it will be called primitive, but they don't have to be disjoint. So why do we talk about renormalization? This helps explain the existence of Mandelbrot sets everywhere. Okay. When I say everywhere, for example, if we look at the Mandelbrot set itself, then you're able to find copies of itself at all scales. And here, this is a theorem by Doherty and Hubbard that states that essentially, if we have a map that is a quadratic map on, so this is some parameter C star on the Mandelbrot set. So F C star is renormalizable with some period P. Then we can actually enlarge, there exists a subset M that contains this parameter, in which on this subset, every map is also renormalizable with the same period. Okay. And then also we can look at the straightening map associated to this subset. And then the straightening map is going to be a homeomorphism onto the Mandelbrot set itself, the original Mandelbrot set. Okay. So here's a picture of the Mandelbrot set in the middle. And then if you try to zoom in at some locations, you see that, well, really, you see that there are subsets that really look like the original Mandelbrot set. So this is a primitive copy in which basically parameters are in here. Well, I guess you have to chop off some of these branches. But you pick any parameter here, it should be renormalizable of some period. I think, if I'm not mistaken, it's 6 or something. Okay. Or maybe 5. Yeah, anyway. On the right here, this is a satellite copy. It looks a bit different because the cast of the Mandelbrot set actually corresponds to the root of this hyperbolic component here. So so it looks a bit distorted near the cusp, but everywhere else is actually quasi-conformally equivalent. Okay. And then you can also see so here on the left, this is a primitive copy. And then if you pick a parameter here, then this is the picture of the Julia set. Okay. And then actually this disk, little disk in the middle here, this corresponds to the field Julia set, the first renormalization. Okay. This will be mapped here, it will be mapped here, somewhere, and then here, and eventually it will come back. And then on the right here, this is a satellite picture. This is the Doherty rabbit. And then essentially we have satellite renormalization with this black disk in the middle here as the field Julia set of the renormalization. This will be mapped onto this, and then it'll be mapped here until it comes back here. So it has period 3. Okay. And then they're all touching at this particular point. This is actually a fixed point, a repelling fixed point. So now going back to the problem of MLC. So if we have a parameter C in a Mandelbrot set, we say that this is infinitely renormalizable if it is contained in an infinite nest of baby Mandelbrot sets. So you start with a Mandelbrot set, and then you find a copy, say M1, all right, a smaller copy, and inside a smaller copy, there's an even smaller copy, say M2, and you can keep going and going, right? And then within this nest, you take the intersection, and then you find a point C, and this is going to be called infinitely renormalizable. Okay. So there's a powerful theorem by Yokos back in the 90s that states that if C is not infinitely renormalizable, then in fact the Mandelbrot set is in fact locally connected at this point. Okay. This is a very powerful theorem, and Yokos here, he basically pioneered the use of puzzles, basically a way of getting some kind of Markov partition on the Julia set, and really studied these puzzle pieces, how they basically how to there's also a notion of modular of these puzzle pieces and so on and so forth. And then yeah, so from this theorem, really the MLC conjecture now is reduced to the parameters in which they are infinitely renormalizable. Okay. And also with a bit of work as well, MLC is also equivalent to the following conjecture. This is called the combinatorial rigidity conjecture. Okay. And it states that if you take any infinite nest of baby Mandelbrot sets, okay, you try to zoom in again and again and again and again, and then every infinite nest must shrink to just a point. It doesn't shrink to some non-degenerate continuum. It shouldn't have an interior. It should just shrink to a single point. Okay. So that's basically the conjecture. And yeah, so for the rest of my time, I'm going to talk about some of the developments of this conjecture. Well, I'm not going to give a complete history, but yeah, we'll see. So there's also a notion of what we call a priori bounds in this framework. So suppose now that we have a quadratic map FC that is infinitely renormalizable. I'm going to keep track of my periods. All right, so there's a period of renormalization, P1, and then there's also P2 for the next level, and then P3 for the next level again, and so on and so forth. All right, so here in what I've drawn here, this is a period 3. Okay, but this is just the first renormalization, let's say. So within here, there might be the next renormalization. It might have some period, okay, and in the total, it will be, say, P2 or something. And then we say that FC, so this quadratic map has a priori bounds if for any n, so for n, you can find the nth renormalization, well, so which means that you can find these disks un gets mapped to vn so that it satisfies this condition. So I'm going to try to explain what this condition is. So we have un, it gets mapped to vn. This is a quadratic-like map. Okay. And then this W quantity, this is the extremal width of the curve families connecting the inner and outer boundaries of this annulus. Okay. So extremal width, if you're familiar with the extremal length, this is dual to that. This is reciprocal, so 1 over the extremal length. You can also view it as, basically, this is a conformal invariant that governs how close the inner and outer boundaries are. Okay, if they're very, very close, they're like, kind of want to pinch together. That means that this W, this width, is very, very high. Okay, so what the statement is really saying is that no matter what n you take, we should have some definite distance between the inner and outer boundaries, essentially. And then analytically speaking, this means that up to affine rescaling, these renormalizations that we take here, it must be pre-compact. So any sequence, and then we take a limit, then it should be, again, a genuine quadratic-like map with some definite moduli here. Okay. Any questions so far? You all have been very quiet, but yeah. No, it's just topological disks. It's just topological disks. Yeah. They don't have to be round. By no means we can guarantee that. That's very special. Yeah. Okay. So the main theorem that I would like to cover is the following. So if we assume that this infinitely renormalizable quadratic map has bounded combinatorics. So bounded combinatorics here means that basically the periods of every at every level is uniformly bounded. Okay. Then we had the two statements that F in fact has a priori bounds, and then also this will imply that the manifold set is locally connected at this point. Okay. I will explain. I will explain in a bit. Yeah, I'm not going to assume anything. Yeah. So yeah, historically, this is not a new theorem. Okay. There were some developments, I think, earlier by Dennis Sullivan when C is real, and then I think later on by Misha and also I think Michael in your thesis for real maps. But generally, Jeremy Kahn proved item 1, assuming that every normalization is primitive. Okay. And then later on, well, this is more recent work by Dima and Misha that proved that actually the proof that Jeremy Kahn had can be generalized to satellite. And then this can also be combined with primitives, and that basically settles number 1. Okay. So the proof here for Jeremy and also Misha and Dima, they were proven in the degenerate regime. Basically, you want to try to study in some sense, services that are very close to degeneracy. And then you want to try to encode them in terms of what we call Witter-Art diagrams and whatnot. And then item 2 here, so how is this related? So there's a paper by Michal Lubitsch back in the 1990s that basically proved the application under what we call the SL condition. So the SL condition here means that this is called the secondary limbs condition. It basically means that the renormalization combinatorics that we have should be contained in finitely many secondary limbs of the Mandelbrot set. What I can say briefly is that this condition is weaker than the bounded combinatorics condition, okay, and therefore it lies within this framework. What I'm gonna do is I'm not gonna explain the proofs behind this and this. I'm gonna talk about new proofs of these two statements. All right. So number 1, I will try to explain a new alternative proof using what we call the totally degenerate regime. And then number 2, I'm also gonna try to explain a new approach using Teichmüller's theorem that hopefully I will have time to cover at the very least maybe 5 to 10 minutes. So this is everything here that I'm going to talk about is joint work with Jeremy Kahn. And then here I'm hoping that, we're really hoping that the new approaches here might be able to generalize to the unbounded case. And we're also very confident number 2 here can be generalized to those that actually do not satisfy the SL condition. Okay. Okay. So that's the plan. So I'm just going to try to explain the proof using a particular example, just to really explain the big ideas behind it. Okay. So I'm going to pick the stationary airplane combinatorics, right? So if you had the manifold set, you can try to zoom in at the parameter containing -1.7 roughly, and then you see that there's a copy of the manifold set here, right? Actually, if you pick any parameter here, it looks a bit like what I've drawn over here. Okay, it has period 3, right? And then what you can do is, within this copy, you can also find the airplane copy again and zoom in over there, right? So from here, you can zoom in again, and then you can repeat this construction and really zoom in at all scales. And then we're gonna pick our infinitely renormalized parameter to be within this nest, to be within this infinite nest. Okay. And then let's see what happens. So if you pick any parameter in the first copy, then this is basically what I've drawn on the board. Okay, so inside a bigger Julia set, there's a little Julia set that I'm going to denote by K10. So this corresponds to the first renormalization. It's going to map to the left and then to the right and then cast back. All right. And then if you go on to the second level, then the one in the middle is going to be split into 3 in some sense. And we're going to get the second renormalization. And then this comes with the little field Julia sets here, K20. And then here, this is going to be a cycle of 9 little Julia sets permuted, and it eventually comes back after 9 iterations. Okay. And then again, if we go on to the third renormalization, then this little Julia set in the middle, say, or any of them really, will be again split into a cluster of 3 of them. Okay, so now you get 27. Now you really see what's happening now if we keep zooming in again and again and again and again. Okay. So here the period is going to be like 3 to the n, really. So from 3 to 9 to 27 and so on and so forth. And then, so the notation I'm going to use is I'm going to use curly kn as the union of the little Julia sets at level n. Okay. And here usually I'm just going to denote kn0 as the central one, the one that contains the critical point. And then kn0 gets mapped to kn1, and then kn2, and so on and so forth. It's going to get permuted. And then I'm also going to consider the hyperbolic geodesic of, so we have the plane, and then if you remove these little Julia sets of level n, right? So we get, well, we can endow it with a complete hyperbolic metric. We can consider the hyperbolic geodesic that goes around each of these little Julia sets of level n. Okay. I'm going to denote it by gamma ni. And then you can consider the length, the hyperbolic length of each of these geodesics, but I'm going to normalize it by multiplying it by pi. And then for the central one, I'm going to denote it by lambda n. Okay, I'm going to denote it by lambda n. So this is roughly the picture. So for level 2, say, like this one, then there's a unique hyperbolic geodesic that goes around. This is gamma 2. For level 3, then it will get smaller in the picture, and I'm going to denote it by gamma 3. So what's the point of all this? There are some basic properties of these hyperbolic geodesics. For one, so all of these KNIs, they are related because KN0 gets mapped to KN1 and so on and so forth, right? You can try to spread it around, or even you can take a pullback or something. And then by basically some elementary application of source lemma, we have that all of these hyperbolic lengths multiplied by pi are really comparable to one another. So here the lambda is a maximum 1, and at the very least it can only be at the very least is lambda n over 2. And then the next thing, so this one, the second property here is a consequence of the straightening theorem that says that there exists some constant. Actually, this constant depends on the period, but it's constant here such that for all n, all of these lambda n's, as you take n going to infinity, they can only grow at most exponentially. Okay, so lambda n plus 1 is at most some constant times lambda n, right? This is not going to be very useful in actually this example, but it will be useful if you consider the satellite combinatorics. Okay. So yeah, what do we do with this? So a priori bounds is more or less, it can be restated as the fact that these surfaces, that the plane minus these little Julia sets at level n, they have uniformly bounded geometry. They have uniformly bounded geometry in the sense that, so we have all these little Julia sets, right, of some level n, say, but you don't want them to really crash to one another. You don't want them to be very close with one another as you take n going to infinity. And in some sense, we can try to measure what it means by uniformly bounded geometry in terms of the boundedness of these hyperbolic lengths. Okay, so each of these will have some definite hyperbolic lengths. And then if we want to try to prove the theorem assuming the contrary, which means that now these hyperbolic lengths will actually go to infinity as n goes to infinity. Okay, which means really that in the limit, these little Julius may actually come very close to one another. Something might go wrong. So if we assume the contrary, we can take a subsequence that are record high. So record high is going to be basically a sequence of times n1, n2, n3, and 4, and so on and so forth, in which all of these hyperbolic lengths, so lambda and k here, is going to be the maximum one compared to the previous ones. Okay, and then because we assume the contrary, we also assume that they actually go to infinity. These hyperbolic lengths go to infinity. And then the strategy is that we want to try to study what happens when these surfaces really, what's going to happen to them as k goes to infinity. Okay. So maybe a bit of intuition before I try to move on. So we have these little Julia sets, and I'm just going to focus on, say, a single GOD set. So here we have C minus capital Kn, or K and K, right? And then we have the single GOD set. And then you can consider the annulus cover of this. So there exists an annulus. And then this is a covering map, a holomorphic covering map. Okay. So that it opens up all the other GOD sets, everything else, but this one. Okay. And then this annulus, okay, let's call this, I don't know, A or something. And then actually the width of this annulus. So when I say the width, it means that it's the extremal width of the curves connecting the interior and exterior boundaries. This is going to be precisely equal to the lambda nk. Yes. So this is again equal to pi times the hyperbolic length. From here, no, from some annulus onto here, Okay. Oh yeah, my bad. So yeah, the inner one here corresponds to the little field Julia set here. And the outer one just basically, it records, how can you go? I guess like you can go here, it can go here, it can spiral around, and that will correspond to some end, let's say. Okay. So how do we study this limit? What we want to do is there are a few subtleties that's going to happen, which is that as we increase k, then of course the number of little Julius is going to increase. Okay, it's going to go very, very far. And then one natural thing that we can try to do is we want to try to control the degeneration as we go really far, in some sense. So I'm going to denote by phi and s by the disk bounded by this hyperbolic geodesic. So basically you have some, say, scale n, and then we zoom out, say, s times. We zoom out s times. Okay. And then the first lemma that we really need is that, so for any s, so s here is basically like how far you zoom out in some sense. And then you can pick any sufficiently high k so that if you have any little Julia set that is contained within this disk, right? So you have this level nk, but then you zoom out s times in some sense, right? Then we have a control of the width of, so we have the control of the extremal width of curves connecting the boundary of the nks and this little Julia set. Okay, so the picture here is that if you zoom out twice, then this geodesic will basically capture 9 little Julia sets. And then you pick any of them. So you pick this one, say, and then you want to try to measure how far, if you want to travel, say, you pick any curve from here to this boundary, this yellow boundary. So if you measure the extremal width of these curve families, It's actually going to be bounded above by this quantity. And then how do you read this? It's basically, so we still have this, lambda nk, right? This is in some sense the measure of degeneration at level nk. But then we also have this factor here. The 24 doesn't really matter, okay? It can be any uniform constant, but this 3 to the minus s over 4 means that it will decay exponentially as you, zoom out, okay? It will decay exponentially as you zoom out. And here the proof that we use here is an application of quasi-additivity law and the covering lemma. What this really is that, roughly speaking, so we have this, curve family connecting, so ki to this, orange curve. But then this I is not very special. You can pick another one, say this one on the right or this one on the right. Okay, so we have a bunch of these curve families, and they sort of interact in a very weird way. But if you want to try to sum them up in some sense, you have to use quasi-additivity law. And the reason why it's not as easy as it gets is because there are some curves that will actually, like, in order for you to go from here to here, you might actually have to go through either of these little Julia sets or something. And then there's just some combinatorics that come into play in the proof about this is all summed up by the quasi-additivity law. And then the covering lemma basically tells you the relation between, say, I and then another little Julia set J. They're actually all comparable, but this is thanks to the covering lemma. Okay. But the main upshot of this is really the exponential decay as you zoom out. Okay, as you zoom out, really, you shouldn't really see this orange boundary very much relative to this level. Okay. And then the next thing before I move on is I have to talk about what we call the control of waves. So all these little Julia sets, well, at the very least over here, this is connected via, so there's some remnants of the Hubbard tree here. So there's like an arc that connects this little Julia set into this one, and then this one into this one. It's almost like a reline, okay? It's not gonna be a Hubbard tree. We don't quite know. A posteriori, we will know, but we're just gonna call this the Hubbard continuum. So the Hubbard continuum is really just the smallest compact connected set that is forward invariant. It connects all the little field Julia sets. Okay. So for this one, it'll be, say, it's like a reline in some sense, but in general, it can be anything. Okay. And then, so the second lemma that we need is that, so if we consider any proper lamination, so lamination is really, just think of it as a collection of disjoint curves within this surface. So this is again, the complement of the little field Julia sets, but then you only zoom it up to level S, really. Okay, and then suppose that this curve family, so this lamination here, every leaf will intersect the Hubbard continuum at least m times. Okay. Oh, this is from the previous notation. I think that's a picture. Yeah. So in this case, when S is 2, then you zoom out twice. You zoom out twice. Okay. You just don't want to go too far, really. If it goes too far, we have the control from the previous lemma. But once we restrict ourselves to some level S, let's say, okay, then yeah, suppose this is the the curve family that we have in this example. I think it intersects so this is the Hubbard continuum. It intersects 3 times. So m here in this case is equals to 3, right? But yeah, we also have a control of the extremal width of this lamination, and the extremal width here is so again there's this factor lambda, but then the most important thing from here is that there's this factor m to the minus 2. And in particular, as m increases, then this actually will decay quadratically. Okay. And this is not really very complicated. In some sense, this is a bit like the most important thing that you do is this. So we have a bunch of little Julia sets. And I suppose the Hubbard continuum, say, looks like this, let's say. And then we have a notion of, so you pick, say, you consider the complement of this tree, and then we have, part that comes from the Julius set. We have part of the boundary that is, inside of the Hubbard Julius, the Hubbard tree. Okay. And then if you pick any two that are non-adjacent, say this one and this one, and then you consider any, family of curves that connect them to. Okay. This is what we call a wave. And actually, we have a uniform bound on the extreme width of each of these objects by some constant times this, this normalizing constant lambda. Okay. It doesn't have to be this one. You can also go from a side of the little Julius set, say this one, and then maybe it goes here or something. Okay. This is maybe another possible. And again, this will be, or it shouldn't intersect this. Again, it should be bounded above by some constant times this lambda nk. And if you manage to prove this fact and then do some kind of decomposition in the end, you also get this control. Okay. What this is telling you is that if it intersects the Hubbard tree too much, okay, then you pay a toll. The width cannot be too high. Okay, the width cannot be too high. It must be bounded above. It's just decay. So in particular, this sort of controls any degeneration that comes from like spiraling too many times. You have to pay some toll. So where are we really going with this? Okay, so the spirit of the total degenerate regime is that, so we have these surfaces, okay, and then we want to see what happens as k goes to infinity. But then the main problem with this, though, is that now the number of this is going to grow as k grows. Okay, in the end, what we're going to get is some kind of infinite type surface. So a disk, no, a plane that has infinitely many holes. Okay, and then to really take the limit, it doesn't make any sense too, because all of these little Phil Julius, they're not necessarily compatible with one another. So you want to try to take a limit in some combinatorial way. You want to try to take a limit in some combinatorial way. So we want to try to build a model as to what happens if you try to zoom in and take the limit. Okay. A posteriori, this actually exists. We do have an actual limit. When you try to zoom in, we have a sigma proper limit. This is a theorem by, I think in one of Kurt Macmillan's books. We can try to construct a model in a somewhat naive way. So here, I'm going to denote by delta. It's going to be a countable disjoint union of disks, and they're discrete. Okay. And then I'm going to denote by delta k to be those disks that are contained in the round disk of radius k. And then here, we can also build a this map f. This is going to be, it's not going to be holomorphic anymore. This is just a topological map. And then here, when we say sigma proper, it means that this is going to be an infinite degree branch covering that comes as an exhaustion of finite degree branch coverings. And then it also fixes every component of delta. And then this is our combinatorial model. This is the presumed geometric limit. Okay. So a priori, we don't know if the actual limit exists. Okay, so this is just going to be some kind of toy model in some sense. This is just a topological model. And then it has the property that, it is equivalent with our map for level k. So the picture is the following. So on the left here, this is what happens before they take the limit, say some level n, some level k. And then say we zoom out twice, so we have these 9 little Phil Julius sets. Okay, and then if we, okay, this is not quadratic-like anymore; it's polynomial-like. But on here we can extract out degree 2 to the 3 to the k map here from say u nkk to v nkk. I think in this case, I only pick k to be technically just 2, really. But really, there's an equivalence between the left and the right. Okay, and the right here, this is our topological model. This is our map, big F. And then in all these little disks are contained in delta. Okay. And then by Thurston equivalence, it means that in some sense, this is almost like a conjugacy, but not really, because technically our little Juliuses are not preserved. In some sense, they are just blown up to just simple disks. Okay. Right. And we're just gonna be transferring any data from the left to the right to our model on the right. Okay. And then on the left here, it does come with a complex structure. Okay. And then on the right, this is just some model. And then we can transfer the complex structure on the left to the right. Okay. So we can do that. So I'm gonna denote the induced complex structure by rho k. Okay. And then in some sense, as we take the limit, so we want to try to take the limit as k goes to infinity. And then what happens with these complex structures is that after rescaling by this factor lambda nk up to this up to this width lambda nk, we will actually get a meaningful data. This is going to be a combinatorial data. This is going to be a proper measured lamination. Proper measured lamination that we're going to denote by big C with a measure mu on this plane minus infinitely many disks. Okay, C minus delta. And then roughly the picture should be like the following. So here I only draw 9 disks, but should think of like infinitely many disks marching to the left, to the right, something. Okay, and they're discrete. And then a proper measured lamination here means that so lamination by proper here, it means that we have a collection of the joint curves coming from, say, a disk to another disk. Okay, and the measure is basically really just a measure on the collection of leaves in the lamination. And then it also has the meaning that, so how do we really get the limit? The meaning behind the limit is the following. So before we take the limit, this is the picture, say, on the left. Okay, and then on the right here, this is our model. Okay, so from the left, it comes to the complex structure, and then we have a notion of extremal width of, say, curves that are going along, that they are homotopic to, say, alpha, which is a proper arc in blue here, for example. And then this has some data, which is the width, the extremal width. And then if we divide the extremal width by lambda nk, and then we take the limit as k goes to infinity, okay, then actually this will converge to the measure. So this is gonna be a measure of C, of the leaves in C that are basically homotopic to alpha itself. Okay. I hope this makes sense. If you have any questions, feel free to ask anything. So yeah, you should think of this, lambda nk as the normalizing constant. Yeah, we have to take a bunch of subsequences for this to really make sense. But in the end, this is really gonna be a genuine limit, not lim sub, not lim if. It's really genuine limit. Okay. And then also here, I say that lambda nk is the is the extremal width of this covering annulus. And then what really happens in the in this model really, so we have this delta, and then we have the lamination C, or this is a bunch of leaves. And then it can go far too, it can go to other disks outside, and so on and so forth, right? And say this is the central one that has the critical point. And then you can consider, maybe I'll draw a bit more. You can consider something analogous to this geodesic. Okay, this geodesic covering the one that contains the critical point. Okay. And then you can also measure the weighted intersection number of this, this measured lamination with this geodesic. with this curve, okay? And then basically, so if I denote this by, I don't know, say gamma 0 or something, and then the intersection number, the weighted intersection number, is really just gonna be 1. It's really just gonna be 1, okay? And the reason comes from here, in some sense, it encodes all, so the width of basically the curve family is going from here to everywhere else, okay? Here to everywhere else, okay? And then it's roughly gonna be, say, lambda nk minus some, maybe some constant. But this constant is really gonna shrink. It's gonna be very small compared to this one as we take the limit. And so if we divide it by lambda nk itself, it's gonna converge into 1. Okay. And then the next thing that we can do is we're not really just happy with this measured lamination. We can also extract out lamination inside the little disks. Lamination inside the little disks. So inside each of the disks in delta, we can also fill in this lamination. So we're going to call it a big lambda. Okay. And then this will give us compounds lamination. And then I guess the rough intuition should be something like this. And then to give you a bit of a meaning behind this, so okay, I'm just going to try to reuse this picture. So here we have the external leaves, but the way we draw the internal leaf is the following, which is that we can try to connect from here to here whenever let's see, what other colors do we have? So this, say, it joins, say, an external leaf to another external leaf. Okay. And then this basically encodes the fact that before we take the limit, so we have these, say, little field Julia sets, and then you have a corresponding analogous curve families that in some sense have the same homotopic class in that it has an external arc that goes from this little Julia set to here, but then it sort of goes through and it goes to some other one. It goes to some other one. So if we measure this, and then if the extremal width is going to be degenerating along in the sense that, going to be comparable to this, right? Then we're going to draw this arc. We're going to draw this arc. That's roughly the intuition. So this is somewhat different compared to, say, like, not necessarily, because it might also capture more. Yeah, it can capture more, because in some sense it can also capture how, say, these little Julia sets are crashing to one another, but then through another little Julia set in some sense. Yeah, that's one way to think about it. Okay, that's the rough idea. So you may ask, okay, what's the point? What is the point behind this? So we can try to define a notion of modulus. So here we have a measure that is on C, which is the external leaves, okay? But we also have these internal leaves, right? That gives us some kind of trajectory as to how they move in some sense. Okay. And we can try to make use of this and define modulus for arbitrary natural paths. So a natural path here, when I say natural, it means that we have a concatenation of external with internal, external, external, so on and so forth. So this is one example, okay, where we have this one, it goes inside and it goes out and inside and out. Okay. This is what we call natural. Okay, just going along, really, just going along. And then whenever we have a natural path, and then if we also consider a function, just any function rho on C on the external leaves, right? So for each external leaf, we're just gonna assign a number, a non-negative number, okay? And then we can sum up these numbers of the external segments, and we get what we call the row length. Okay, the row length is really just a sum of the, essentially the row weights of the external segments. Okay, so we don't really assign any weights to the internal ones, just the external ones. And then from there, then we can assign. So we have this notion of length, and then from here we also have a notion of modulus. So this is pretty much a generalization of modulus, like extremal length in some sense. But here this will be the reciprocal. So this is gonna be like the extremal width in some sense. Rho is just for the external ones, yes. But then here it's also different because the natural path family, it also includes the combinatorics as to how they go through the internal ones. So the internal ones only tell you like how do you go in some sense, right? The external ones is the one that gives you the weights. Okay. So so here the definition again is just the infimum of the row area, and here again this is really just with respect to the external measure, okay. And here infimum across all the possible functions row that you can take, so that the row length of each leaf is at least 1. Okay. So really, if you've seen the mu is the measure of the external measure. Measure of the external leaves, yes. Okay. And then if you define modulus this way, then we have the usual properties of modulus, say parallel law, series law, and actually we're also able to get an analog of the covering lemma and the quasi-additivity law in this framework as well. Okay, this is in some sense the combinatorial framework. Okay. And then another property that I haven't really talked much about, the dynamics. So this is where it comes in. Okay. So we have a modulus on this compound lamination X, but then we can also pull this back. Okay, we can pull this back, and I think I have the picture here. Okay, so so when you pull back X, then we have this, F upper star X, and this is gonna be again a compound lamination, but then the distance is gonna be much more, because we have some pre-images of the, I guess in some sense, the little Julia sets. So here this is gonna be like the pre-images, okay? And then, so this domination property here essentially says the following, which is that if we pick any natural path family along X, so say this one over here, then we can also consider a similar path family for F upper star X. And then similar here in the sense that over here on this guy down here, if we forget the pre-images, okay, then it should be homotopic to the one above. Okay, it should be homotopic to the one above. So here we can just forget this, forget this, forget this, forget this. Okay, it's really similar. And then we have the domination property that tells us that really the X modulus of gamma is actually bounded above by the modulus with respect to F upper star X. Okay, and then the way you should think about this is really just coming from the fact that, well, delta is forward invariant, okay, and then naturally then this should be contained inside the pre-image. Okay. So there's some kind of containment. It's roughly speaking, naively speaking, this is basically like Schwartz lemma, but of course, there's a lot of estimates that come into play to really realize this. And then, okay, so this is basically our TOR model. This is our, like limiting lamination, and then we can extract out some kind of, in some sense, some notion of modulus to this combinatorial data. But then ultimately, we want to try to prove a priori bounds, which means that we want to try to get a contradiction out of this, this weird thing that we have created. Okay, so to get a contradiction, we want to try to consider a path family that comes from some scale and goes back to another this fixed scale again. So if you fix scale S, right, we can consider XS. So XS is going to be all natural paths along X that come from delta S to delta S. So here, this is when S is 1. Right? When S is 1, you zoom out once, we have these 3 little Julia sets. And then along this compound lamination, say you go out, and then you trace along, and then it might come back to delta 1 again. And then when you do that, this is going to be our system, say X1. Okay. And then what we're going to do is we're going to introduce, so there's a data as well that comes from the Hubbard tree. But then as we take the limit in our combinatorial limit, the Hubbard continuum might actually be kind of weird. So we only we really just extract out the homotopy data, right? So this is really roughly like the homotopy Hubbard tree. And then what we really want to use is not really the Hubbard tree itself, but rather the dual. So the dual of this will be, it's going to be, so I guess in this case, at scale 1, the Hubbard tree is like this connecting that and then connecting that. And then the dual of this Hubbard tree is going to be really these two bivertical curves, right? This one and this one. Okay, so this is going to be the HS perp or H1 perp in this case. Okay, and then you can consider the weighted intersection number, right, of this returning family with this. And then there are a few observations that you can make. So if you zoom out sufficiently enough at a sufficiently large scale, I think here I put 12, but actually it might not be necessary. This weighted intersection number is going to be positive, but more importantly, it's going to be finite. Okay, so a priori, this guy, there might be some curves that go very, very far, but then it might, it will come back. It might not be obvious that it's going to be finite, but in fact, it's going to be finite. Okay. And then the domination property actually implies that we have this inequality that relates the weighted intersection number of X with the F alpha star X. Okay. But then there's also the data that comes from the homotopy Hubbard tree itself. Am I running out of time? Oh, over. Oh, I'm so sorry. Okay. All right. Okay. Yeah. All right. Yeah. So the forward invariance of the Hubbard tree actually implies that in fact we have the opposite inequality. Okay. And this, these 3 facts will actually imply that really this is a contradiction. And then maybe just to wrap up, the last one. So the example that I told you, this is the primitive case, but if it's satellite, then the difference is really that these little Juliuses will actually touch, okay? And then they will form a bouquet of little Julia sets. But you can still play the same game, really. You can look at, say, probability geodesic going around these little bouquets and everything. And the final conclusion will still be the same. There are some additional arguments, but there are very little modifications, and you can still play the same game. So yeah, there are a few more slides, but I think, yeah, that's basically it.